some questions from Chem 101. Is that okay with you guys? Or do you guys have any questions regarding what you guys have learned so far?
Yeah, we can go over that stuff. That's fine.
No? Okay. Well, I guess we can go over one of the questions. And here, let me type it up. Perfect. So let's start again. I'm sorry. So what are you given, and what are you looking for here?
So you're looking for the longest wavelength of light.
Okay, so want wavelength. And then what is that signal that goes with wave, or symbol that goes with wavelength?
Lambda.
Lambda, yeah. Right? Yeah, lambda. And they wanted in nanometers. And then you're given what?
6.35 EP.
Okay. So then from then on, what do we know? Just what you've learned so far. So what can we do with this information? With energy, right? And wavelength. What comes to mind?
I remember E is equal to C times lambda divided by, C times H divided by lambda.
Okay, so C times H, let me write this. So C times H divided by lambda, you said?
Yeah.
Okay. Which equals what?
E.
E, right? And then, but here, what are we trying to find?
Our wavelength.
Our wavelength, right? So then, when it comes to chemistry, and you guys have seen this all throughout chemistry, right? What do we do with our equations?
We move it around.
We move it around to our liking or to whatever we want to find. So here in this case, we want to find, like you guys stated, lambda. So how can we get lambda by itself? And this just turns into just like a regular like manipulation of equations. How do we get lambda by itself?
Would you multiply the y to get it to the other side?
The y. Which y?
Or the lambda.
Right. There is this math trick that is, for me, hopefully for you guys too, it's just easier. So let's say you have the symbol or whatever you want to find is at the bottom, it's at the denominator. So what we're going to do, we're just going to flip both of the sides. So we're going to say lambda over CH is equal to 1 over E. Okay. And then from there, we have this equation. So we just flipped it. Okay, so then from there, if we want to get lambda by itself, what do we do?
Multiply.
Right, multiply what?
CH.
Right, CH. Right, and we're left with lambda is equal to CH over E. And then C standing for what again? You can remind me?
Speed of light.
Speed of light, and speed of light is equal to
2.998 times 10 to the 8.
It's 10 to the 8. And what are our units? Remember, units are very important.
Meters per second.
Per second. What about H? What is H?
Planck's constant.
Planck's constant, right? And then what does H, or what is the value for H?
I
That's
believe it's
626.
Right, Cassie, 6.626, like Lilo and Stitch, 626. I don't know why that just came to mind. Times what?
10 to the negative 34th joules per second.
10 to the negative 34 times joules times seconds. Okay, so then from there, we're given our work function or our energy right here, 3.35 eV, but you're also given this conversion, right? So what are we going to have to do with that before we actually plug everything in?
Convert the 6.35 EV into joules.
Right, you're going to convert it into joules. So, we always want to start with what we want to convert. So 6.35 EV. And then from there, what do I put in my denominator?
1 EV.
1 EV. And at the top, obviously, the 1.6 times 10 to the negative 19 joules. Right? This cancels out and you're left with joules. So if you plug that into your calculator, what do you get? Six times 10 to the negative 19.
1.02 times 10 to the negative 18.
Sorry, can you repeat that? 1.0.
1.01, or sorry, 2 times 10 to the negative 18
Yeah, good job. And what are our units again?
joules.
Joules, yep. All right, so are we ready to go and just plug everything in? Or do we have to do anything else? What do you guys think?
No, I think we're ready to plug in.
Yeah, we're ready to plug in. We have everything now. We have our E, we have our C and our H are our constants, so we have that already. And we manipulated the equation in our favor. So then, yeah, we just plug everything in. So I'm going to delete this bottom part. So then we have lambda is equal to our C constant, which we said was 2.998 times 10 to the 8 meters per second. Our H, our Planck, which is 6.626 times 10 to the negative 34 joules times second, over our energy, right, which we found it to be 1.02 times 10 to the negative 18 joules. So as you can see, right, our units will eventually cancel out. And when you plug all that into your calculator, what do you get as an end result? Plug it in.
1.95 times 10 to the negative 7.
Oh, good job. That's what I got as well. So 1.95 times 10 to the negative 7. And what are our units? If we cancel everything off, well, what needs to be canceled off?
Meters.
Meters, right? And are we done here?
No.
No, right? No, so what is the final step that we have to take in order to get our answer, our final answer?
Convert the meters to nanometers.
Right, convert the meters to nanometers, right? Because they tell you here in the question. So let's do that. So again, what if we want to go to meters to nanometers? What would be the unit conversion for that? Oh no, goodness. What would be the unit conversion for that?
1 meter equals 1 times 10 to the 9.
Yeah, 1 times 10 to the 9. We want to go from meters to nanometers. And again, this turns into another conversion. So, and you guys, I mean, you've seen this in Chem1A. Units are very important and to keep track of. So we found out that we have 1.95 times 10 to the negative 7 meters, right? That's our wavelength that we found. And then we just treat it as a regular conversion. So we have 1 meter at the bottom and then 1 times 10 to the 9 nanometers at the top, giving us a whopping
1.95 times 10 to the 16th.
1.95 times 10 to the 16th. Let's see. So we have 5.
Oh, I didn't put negative. Never mind.
Yeah. 195. Is that what you all got?
Yeah.
Yeah. Okay. And how many sig figs? Because remember, sig figs are also important. How many sig figs do we want?
3.
3 sig figs, right? So we have 195, and we found it to be nanometers. Okay. So does anyone have any questions regarding this in anywhere or any step?
Nope, I'm good.
Okay. Right, yeah, don't forget to go to tutoring, you guys. I am the SI. I know some of you, but you know, even if you don't have the questions and you want to do homework during that time, you can just hop in. But yeah.
Yeah, she gets paid either way, so.
Do we
Yeah.
have to register in that other class, like the N100 or whatever?
NC 100, yep.
Yeah, you have to register for that. But
And you want to be sure to register for the one in Coalinga, not Lemoore.
yeah.
Okay.
And also the link is on Dr. Henry's syllabus, like from 6 to 9. So if you click on the link, it's going to take you directly to my Zoom meeting. And if you guys do that, I can help you kind of set up the NC 100 for you guys if you guys go. Yeah. Right. Well, Dr. Henry, it's all yours, I guess.
Okay, so last we were talking about Bohr, you know, and Bohr basically had this idea. He made this model of the hydrogen atom and where the electron, that one electron in the hydrogen atom is, right? Now, and I told you guys the last we left off, I wanted you to think about it. Why do you think Bohr's model for the hydrogen atom was great, but after he did the hydrogen atoms, all of the other models that he tried were total failures? Anyone take a guess? Come on, you guys are talkative with Jessica. Now you can't stop talking now.
Will you ask the question one more time?
If I talk too fast, I'll slow down. So I said, why, or can you guys hear me? I'm in my office, so it's kind of weird. Why do you think Bohr's model for all of the other atoms, other than hydrogen, failed? How does hydrogen differ from all of the other atoms? There's two major ways. Well,
Is it because hydrogen can act as a metal?
so it could be, it's the aspect of the characteristics of hydrogen, but like lithium acts as a metal, right? Lithium is a metal. So why didn't his modeling for lithium?
Cassie read
Not
on the
fail.
chat electrons.
That's right. Okay, that is correct, Cassie. So in the case of hydrogen, and actually there's two reasons. One is that hydrogen doesn't have a neutron, right? You guys remember when you guys calculated it a long time ago? I know it's ancient now, right? Hydrogen doesn't have a neutron. It only has proton and the electron, right? Because it only had the proton and the electron, those are the only factors that are taken into consideration. But it only had one electron, where helium has two electrons, right? And then also helium has neutrons that are also playing a role in that orbitation and things to that extent. Okay, so but one of the major things is that when you start getting into the higher atoms, they have more electrons. And so you have to think about the behavior of electrons interacting with electrons, as well as electrons independently interacting with the nucleus. Do you guys understand?
Yeah.
So Bohr's models for all of the other elements fail because electrons. There are more electrons, and you really got to think about, you never account for that electron-electron interaction, and that plays a huge role into things, right? How many of you guys are in relationships? Nobody? All you guys are single?
Yes,
Yeah.
all of us are single.
Okay.
Sadly.
Okay.
Wait, except Cassie. Wait, Cassie.
I'm like, Cassie, is there something I should know? Does Casey know? You know? Cassie's going around, yeah, I'm single now. No, I can't hear you. I can't hear you again. So although you guys are single, you guys have an idea, right? So when you guys are in relationships, you know that you guys have to deal with their parents, the other person's parents, you got to deal with your parents, and you guys deal with each other, right? So you're not just dealing with each other, you're dealing with each set of parents as well too. Is that right? When you guys were in relationships or will be in relationships?
Cassie said, Lord, yeah.
Yeah, so very similarly, that's what the electrons, what's going on with the electrons. And that's going on in the atoms, because it's not just that proton and the neutron that are doing the interaction. It's the proton, the neutron, I'm sorry, proton and electron doing the interaction. It's the proton, the neutron, and the electron. And in addition to that, the electrons all the way around it, right? So all of that has to be taken into consideration, okay? And primarily, the biggest thing is those electrons interacting with each other, how they affect each other, right? Because electrons are negatively charged. So if they get too close together, what happens? You put two electrons together, what's going to happen?
Repel?
It's going to repel, right? And so we have to take in consideration those interactions. So we have to have enough distance for the electrons be far enough away from each other so they don't be shooting around in those orbits, okay? So that's going to be part of it. So that's part of quantum, okay? That's understanding why things work the way they are. Now, the other thing is that the one thing that Bohr did that none of the other people had done before everybody was relying on classic mechanics. Well, you can't rely on classic mechanics because we're working on smaller particles. And so that repulsion is huge for that small particle, where it may not be as big, it can be dampened by all of the other factors in terms of the macro scale things. Okay. And so classic mechanics did not fully describe the things that were going on, or classic physics really couldn't describe it. And so that's the reason why, and Bohr is considered the father of quantum mechanics. That's part of the reason why he had to take a look at it differently. Okay, so let's go and talk about what he did accomplish. So one of the things that he did make apparent was that there's these energy levels where these electrons are able to shoot up to, and also where they're naturally sitting at, right? So you have your ground state energy level for each of those electrons. And each of those electrons technically have a different type of signature associated, okay? A different energy level that they're at, or a different spin, okay? And we'll start talking about more about that. And that's going to be essential for kind of understanding how you can maintain those orbits without those electrons, again, running into each other and causing havoc in the situation. Okay, so the amount of energy, the amount of electron energy will increase the further away you are from the nucleus. Okay, so remember, we have those energy levels, and then which we call the quantum numbers. So that's typically your first quantum number. And we'll talk more about that again here in a second. And then we also know that the further we get away from the nucleus, the more energy it's involved in keeping that distance, okay? And we know that each energy level is discrete. So in that case, we're getting those very single straight lines in terms of the amount of energy that's being released when those electrons are able to drop back down to ground state. Okay, so he won a Nobel Prize for this and for what he had done and his contribution there. But that wasn't the only thing that went on. There are other people who have also contributed to better understand quantum mechanics, and we'll talk about that as well. Sorry to give you the history lesson, but it's important for us to kind of get to that. Where do these 4 quantum numbers come from? Okay, so the thing that we know so far, so we've been building this up. So we know that there was a duality, right? We know that there's the particle wave duality that occurs. And this is one of the things that are occurring with those electrons. It's a particle, but yet it has wave-like tendencies, right? And this is something that was totally different that was observed before. Either you can be a wave or you can be a particle. You can't be both, right? And that's particularly on the macro scale. You don't see waves and particles happening in real life. Now we kind of understand at the micro level, that's what's happening. That's what is really occurring. And so we can kind of explain some of the phenomenon that are existing. And then also in the 1920s, you could only worry about things that you can probably see with your eyes. You're very limited by how small things were, right? And so we're starting to recognize there are different rules for things that are so small than those large objects that we were working with. Okay? Questions, concerns, Cash? This is just the spectrum. The slide is actually in the wrong spot. It's okay. I wanted it to be there so you guys can actually see the visible light spectrum as well. Okay, so when we were talking about the interference pattern and stuff like that, this is an example in the case of water where you have, you throw a pebble in 2 spots and then the waves start to interfere with each other. And so the waves could either be constructive or destructive. If they cancel each other out, they're destructive. If they amplify each other, then they're constructive. Okay, so then that brings us back to that concept of the wave characteristics, because we really haven't touched on it enough, right? We've talked a little bit about that particle, and then how do we accommodate the particle aspects into our kind of wave functions, right? So, Luis, they is it Boyle? Excuse me. So he actually took this a little bit further. He basically says, well, you know, when we're talking about waves, we have to think about it in terms of momentum. Do you guys know what momentum is? Anybody knows what momentum is?
Kinda.
Kinda. So now let's see. How many of you guys watch gymnastics during the Olympics? Anybody?
Sometimes.
Sometimes. Okay. So you know how, you know, the gymnast is doing the flips and everything like that, and then she goes and she does her stand up and everything like that, and she just keeps going and, you know, falls down and gets pointed at, right?
Yeah.
Okay. So what caused her to fall down?
The momentum.
The momentum, right? Exactly. So it was that momentum that caused her to fall down, right? So because, you know, it's a combination of what? You know, if she's going slow, is she likely to go fall down? Or is she going fast? When is she more likely to fall down? Going slow or going fast?
Faster.
Faster. So if you're going really fast, and you see, I've seen them, they're like, right? They do their flip, and then they say, poop, fall right off the stage, right? You've seen that? Anybody seen that, or am I just making it up? So because they're going so fast, right? So we know that means that there has to be something to do with velocity, right? Speed, velocity. Make sense?
Mm-hmm.
Okay. Now, if they're really stick figures, right? They're really light and petite. Are they going to be more likely to fall off the stage? Or if they're, you know, big girls, you know, big bone, who's going to be more likely to fall off the stage? Or big bone guys, you know? Big bone. So the heavier you are, the more mass you have, that's also going to increase your momentum. So if we think about momentum, come on now, work with me now. Oh, you guys are seeing my little screen, aren't you?
Yeah.
You guys are horrible at not telling me. I'm going to start beating you.
I don't think about it.
I like variety.
Okay, so the symbol that we use for momentum is P. P is going to be mass times velocity. So the Boyer basically says that when we talk about the wavelength, right, it has momentum in it. We have to take into account the momentum of the particle, right? And so he says, okay, so then if we have lambda is equal to h m fix my lambda so it looks like a lambda, not an H. Or we could say H over P. Okay. Now this, where V is velocity, and this is not new. Okay. So we can sit there and say lambda is equal to Planck's constant over mass over velocity. And so that was how he described the wavelength. So that you're taking into consideration, of course, that concept of the light, particle and wave duality, right? So the mass, because when we talk about particles, particles have mass associated with them. Okay, you guys with me?
Yeah.
Yeah.
Okay, And so this starts to kind of take into account and resolve that the particle wave duality paradox, okay, or the photoelectric effect paradox. Okay, so this is again another equation that you have to remember. Now, the thing is that Du Bois basically says, oh, we've got to think about this because, you know, Bohr had this great idea about the quantization, right? So if we're talking about an electron, so if we have an electron in the first energy level, well, what about the electron in the second energy level? Is that going to affect the wavelength? Well, of course it's going to affect the wavelength because, you know, that wavelength is going to change in that context because it's further out. Makes sense? Right? And so we also have to start taking into consideration those integers as well. And not only that, we have to take in consideration that it's orbiting the nucleus, right? So it's not just a wave going like this, you know, it's not just a straight line wave, it's actually a circular wave, right? Because it's doing orbiting. So we're having something like this going, okay? So I should probably draw it like, so we have something like this going on instead of something like this. Don't make too much fun of my wave, right? So if it was going like this would be fine, right? It'll be perfect. But we know that we have the nucleus and we have the electrons orbiting. And so, and we have those levels. And so we need to rearrange this equation or modify this equation to kind of accommodate the fact that we have a radial. Remember we talked about radial meaning circular. We have a radial momentum going on, okay? Okay, so the way that we take that in consideration is now we know that there's going to be integers associated with it, and we know that there's going to be it's going to be circular. It's a circular wave. It's not a linear wave, right? So we go, the circumference of a circle, which is 2 pi r, is equal to n times lambda. And that kind of makes sense, right? So the number of wavelengths is going to be equal to 2 pi r, which is the circumference of the circle, right? So we're saying we're taking all of this consideration. So if we added all of the wavelengths together, that should also equal the circumference, right? Yeah, no, maybe. Well, for now it does. So if we plug that into this equation, this modified equation, we end up getting 2 pi r and lambda. So then we can change this where P represents the momentum. We can go N times H divided by MV. And so if we then recognize this L here, this L here is angular momentum. We divide both the top and the bottom by R. I mean, basically multiplying it by 1. R divided by R is just 1, just so that we can get this in terms of the angular momentum. And then we could just modify our equation and say, come on, oops, got carried away. So we know that in classic physics, basically angular momentum is equal to the radius times P, which is radius times momentum. That equals your angular momentum. And this is accounting for that circular motion, okay? So we have the angular momentum that we also have to take into consideration. We break down this equation, and then we basically get L is equal to N Planck's constant divided by 2 pi r, or H over 2 pi is going to be the same thing as H bar. Okay? And so you're going to end up with this equation if we take into consideration Bohr's contribution, okay, for the angular momentum. Are you with me?
Kind of.
Kind of. Okay. So this here represents our circular momentum. This here represents our angular momentum. It's perpendicular to what? So H with the line in it is just going to be equal. I think the former name is, it's the angular Planck's constant. So, oops, wrong way. So this is what H with the line is equal to. You get that, Cassie? Okay, so now we have to, again, keep in consideration all the aspects of the wave nature of electrons. And so there are going to be other contributions that are going to be added onto this. So, and part of that deals with that interference. Remember, we were saying we don't want these guys to really interfere with each other, because if they interfere with each other, wave-like aspect of it, it can also cause other issues, right? So we don't want electrons popping off everywhere, going in every direction. So they continue to do a lot more experiments to try to understand how electrons are moving in an atom. And, you know, and is it really the way it functions? Because a lot of people were skeptics, you know, that we don't believe that crap. And so these were some of the experiments that have been done. And so basically you had an electron source, and they noticed that the electron source had basically made, very generally, patterns that look like this. So, but when they started lowering down that electron source, so that there were only a few of them, so then they were able to sit there and see, okay, so there's a particle aspect of it, right? So it's not just full complete waves that are going. So if it was fully complete waves, then it would look totally like this. We'd have no problems. But if we're lowering down the amount of particles, or the electron source was less, they saw the scattering. But over time, it started to resemble as if it was a total wave. So enough of those particles that are going through, they will act, because they're moving in that wave-like motion, just like a continuous wave that is going on. Okay, you guys get that? So like over time, they saw, okay, we had one particle here, one particle there. But then they start seeing those discrete lines, okay, that you would normally see with a complete wave function. Okay, so again, you know, people were in doubt, and they further proved that it is this wave particle duality, right? So you have these particles that are behaving like waves. Okay, and again, classic mechanics or classic physics, they were just like, blew them out of the water, you know? They're like, this is crap. You can't, no, right? So you have even more people that were jumping on the wagon to try to disprove it, right? And so that brings us to Heisenberg.
The meth cook?
Not the meth cook, but I think it's funny though, right? His name is Heisenberg. And so Heisenberg's uncertainty, right? Okay, so Heisenberg's uncertainty principle basically says that it's fundamentally impossible to determine simultaneously and exactly both the momentum and the position of a particle, right? So we can't do it simultaneously and exactly, because stuff is moving, right? So it's going to be hard for us to sit there and determine the exact location where it's exactly located at and the momentum that's associated, right? So we have to take into consideration that uncertainty, okay? So he basically just established an equation to say, basically, this is the reason why, all of those quantum physicists, they can't give you anything exact, and now that I'm going to become a quantum physicist as well, I'm giving you a reason why we can never be pinpointed exactly, right? And there's a calculation. Come on. Okay, so delta x representing the position, the uncertainty of the position. So that delta represents uncertainty associated with that position it's actually located of the particle. So we can't determine exactly where the particle is going to be located. And we also can't determine, this represents the uncertainty of the momentum, okay? And so the uncertainty of it is always going to be greater than that h bar over 2, okay? And so, and that was basically his contribution, right? So there's uncertainty associated. Now, this is going to be more important later on when we start talking about electron location, okay? So then Trundinger, and what's so funny is, like, I watch a lot of sci-fi movies and TV shows and stuff like that. And a lot of these words, like Breaking Bad, Heisenberg, right? And now you know where he got his name from, right?
Yep.
So Trundinger is also a very common character, right? So if you guys watch, what is it? Marvel's S.H.I.E.L.D., right? It used to be on ABC, I think. So there was a character called Trundinger, right? And they were making reference to Erwin Trundinger. Now, Trundinger basically came up with an equation. And this equation is currently being used today. It's one of the most commonly used equations, and it is a hot mess. So are you guys ready for it? Now, Schrödinger basically said that, we have to sit there and take in consideration the wave-like characteristics of electrons. But, we've been thinking about wave in a two-dimensional fashion, right? Because when we think about it, when we're talking about orbiting, we're thinking about, okay, so here's the center in the middle, and it's orbiting like this, right? In a 2D plane rather than in a 3D plane. Do you guys understand? So, like, for instance, this here represents the nucleus, right? So we know that the nucleus is like a ball in the middle, right? So initially we we're just thinking it's kind of like, okay, it's orbiting in a perfect little circle around the sun or around the nucleus, right? Well, that's not the case. So when they start actually looking at the characteristics of the actual electrons from when they're looking at individual particles, they start recognizing that there's a three-dimensional structure that's associated. And so Schrödinger says, hey, dudes, you guys, we can't look at it just as a circle because it's not just a circle. So we need to sit there and think about it in a more complex fashion. We need to think of it as a 3D wave, not a two-dimensional wave, but a three-dimensional wave. So, you have this going on, but you're also having orbiting that's going around in certain ways, right? And so this is called the wave function, right? And so he basically added this onto the calculation. So our calculation is getting a little more complicated. So then Max Born he basically had also made contributions to this as well. And, they were sitting there saying, again, and this was, again, saying that you guys remember stationary waves. What are stationary waves? Because we talked about them last week.
Stay at a fixed point.
They stay at a fixed point. Okay, so again, so we're working with stationary waves, meaning that it's at a fixed point, but it's a 3D form of that. So these guys are staying within a fixed point or a fixed region. Okay, so these electrons, right, they were sitting there saying are still particles, right? And so the wave is going to be represented by the wave function. Is not necessarily a physical wave, but instead it's just its probability. It's just basically complex probability of amplitudes. Okay, because of this, we need to sit there and try to get rid of some of that uncertainty that Heisenberg was sitting there talking about, right? And so we have to make some modifications to our function even more. Okay, so if you basically take this wave function, takes the absolute value of it and you square it, that's going to help describe that probability that's going to be associated with those particles being at certain locations at certain time and space. Okay. So now bottom line is we have Trundinger's equation. So this H, capital H with the hat, that's called the Hamiltonian operator. So this is just basically, it's a set of mathematical operators that are going to represent the total amount of energy associated with those electrons. And so times the wave function is going to equal the energy, total energy, times the wave function. So basically, energy is going to just be a function of the Hamiltonian operators. Okay. Okay, so all of these guys with their equations, and when you get into physical chemistry, which is quantum mechanics, they'll explain the significance of they'll explain more the significance of the equations in more detail, and then they'll start talking to you about, okay, if you have a turkey in the oven, and in theory, that turkey, under the right circumstances, under the right moment, and could pop out of the oven and end up on your table, ready to be eaten, right, without you doing anything. Now, when we get to that point, that'll be great. We haven't got there yet. So. Okay, so now we need to start talking about the quantum theory in terms of things that we can actually understand and how it really pertains to all of those elements, and how can we start taking the other elements into consideration that have more than that single electron. Okay, and why is it going to be important that we use the aspect, first off, the energy levels, or the quantization, or our quantum number, the principal quantum number, which is that very first one, and how is that incorporated in our periodic table, and how is that incorporated in the element itself, and how can we utilize them? Okay, so we are actually going to stop here and hopefully finish up the rest of the chapter, and then we'll start talking about the principal quantum number and then how it pertains to us for the rest of the semester, and then we'll talk about the next 3 quantum numbers after that. But keep in mind a couple of things that we've talked about today. So we have Bohr kind of discovered the quantum number, so the energy levels. So that represents the energy levels. We've talked about the angular momentum. That's going to be another quantum. So we also need to start thinking about what are the other aspects of those electrons that we have to take in consideration. We have the principal quantum number, we have the angular momentum, and then I kind of briefly gave you a preview, something about spin. So we have spin that has to be taken into consideration, and there'll be one more. Okay, so then keep that in mind for the next couple of days. I'm going to actually have to extend your homework. On Wednesday, I have a full day meeting that I can't get out of. It's an essential meeting. So I'm going to talk to Jessica, and then I'll give you guys an update whether or not we'll be having class on Wednesday or not. Okay. And you're going to have a lab simulation that you're going to have to be responsible for. It's going to be going up, and then that may just be part of what you guys do for your lab period. I mean, for your class period. Okay,
Will that be on Wednesday or today?
Wednesday.
Okay, so do we have to join the lab today?
There's no
or-
lab today. Yeah, because you haven't got. Not everybody has their kit, Cassie.
Okay.
I'm just saying. And oh, wait, and speaking of kits, while I'm talking kit here, let me stop sharing. So some of you guys may be missing components to your kit. The missing components, check to see whether or not you have a copper metal strip. It looks like copper. In most cases, it'll say copper on it. So you're looking for a copper metal strip. You're looking for a stand. You should have a stand and I should say a stand and the base. You should have 14 alligator clips. You guys know what alligator clips are?
No.
Like chip clips.
Yeah, the little, yeah. Yep. So 14 alligator clips. And the other thing that would have been missing was a black piece of cardstock. So if you
Wait, what
don't
did you say
have
was
any of
that?
those, what was that?
What did you say was the last one that we were?
That you may be missing is a black piece of cardstock.
Okay.
Oh, and filter papers. Filter papers for the other thing. Let me write that down. I don't forget. So some of them we ran short and things didn't come in when they were supposed to. And so I had to order from Amazon and it came in. So I'll be able to provide those things to you. So just keep that in mind. If they're missing something, then the first lab will have most of those items for you, but the black cardstock is going to be one of the first labs that you're going to need. So, and we'll be doing that lab next week.
Okay.
So if you're missing any of those items, please let me know and I'll get a little packet together for you.
Dr. Henry, Cassie sent a chat. It says an address.
1645. Yes. Military time. Okay.
Alrighty.
Any questions?
No.
No questions? Okay, I'll see you guys on, well, I won't see you on Wednesday, but I'll see you guys next week then.
Okay.
Okay?
Yep.
You have a good day.